In the previous section, we learned that our instantaneous rate of change, where x is equal to a, is defined by the limit as h approaches 0 of f of a plus h minus f of a divided by h, and we're looking at the values of h that are very small and getting very close to 0. It can also be described by what we call a tangent line, and this tangent line touches our function at one specific point, and our slope is going to be determined by this tangent line, and we're getting our slope from our instantaneous rate of change. All right. So the slope of a tangent line, all right, for some function f of x is at a point A and its f of a or its y value. And this slope is still defined by our limit as h approaches 0 of f of a plus h minus f of a over h, provided that this limit exists. If this limit does not exist, there's no tangent line at that point. All right, so this ends up being undefined for whatever reason. There is no tangent line at this particular point of a function. So when we're talking about a derivative of a function, it's defined as the slope of the tangent line at that point, or more specifically, that instantaneous rate of change. And we're going ahead and defining it right now as a difference quotient. The difference quotient is nothing more than our f of x plus h minus f of x divided by h. So it looks just like our instantaneous rate of change, except we're not trying to find the limit at that particular point as h approaches 0. All right. And so we're looking at, when we have our difference quotient here, we're looking at the slope of a secant line. And this secant line is the line that cuts through the function at 2 points. In other words, our secant line represents our average rate of change that we talked about in the last section. All right. It also refers to our average velocity. Again, very simple, what we just talked about in our last section. All right. And it's also related to our average change of cost, revenue, or profit, which is more of what you're going to be using it for in the business world. When we go ahead and actually talk about derivative, that's where we go ahead and use the idea of the limit as h approaches 0 of our f of x plus h minus f of x divided by h. This is our slope of our tangent line. This is our instantaneous rate of change. This is our instantaneous velocity, so our velocity at one particular point in time. And this also represents, in the business, our marginal cost, our marginal revenue, or our marginal profit. Okay, so our notation that we're using to go ahead and show that it's a derivative is f prime of x, so that little comma represents prime. We either say y prime, we'll use dy divided by dx. We'll use df divided by dx. We'll use capital C prime of a particular number. And the C prime of the particular number, in this case 5, is the marginal cost when x is equal to 5. All right. So for the next two examples, I'm going to show you their graphs. You could see them in page 189. They're number 7 and number 9 in the exercise area. If you want to look at them in your ebook in my math lab, go ahead and do that. If you don't know how to get to your ebook, you can ask and I will let you know how to go ahead and get inside there. We're going to look at number 7 first. And number 7, we just want to estimate the slope of the tangent line. All right. So here is our graph. And what we do is we have our function that's in blue that curves upward. We have our tangent line, which is in red. And we're given the point negative 2, 2, which is that point of our instantaneous rate of change. Right? And what we want to do is we want to estimate the slope of this tangent line. And what we want to do is we want to pick 2 points on this line that you can estimate the easiest. And if you look at this line going through, we could go ahead, obviously negative 2, 2 is given to us, but we want to find a nice point, especially if they're integers. We want to find some points that are going to work best, that will be integer numbers that will be easy to figure out. We have a couple different choices here. If we go ahead and go to the left, we kind of look like we have a nice point that is right here, but that's kind of off the graph. But if we go ahead and go to the right, we see we kind of have a nice point right here at 2, 3. So I'm going to use this point here in black and the point that's given to us and try to go ahead and find the slope of this tangent line. And when I go ahead and figure out the slope, I end up with slope being 1/4. So estimating this slope from 2 points, it looks like that I have a slope of about 1/4. If we go ahead and look at number 9, we want to go ahead again and find the slope of a tangent line. Now you can see our function is again in blue. Our tangent line is in red. And we're given the point -3, 3. But look at what our tangent line is doing. It's going straight across. It is parallel with our x-axis. When we have a line that's parallel with the x-axis, it has a slope of 0. So we don't need to go ahead and pick another point, but we could. And we're going to find that our slope is 0 in this case. Right, so now we're going to go ahead and use the definition of the derivative. We're going to find f prime of x, and then we're going to use that derivative to go ahead and compute the values at -2, 0, and 3, providing that the derivative exists. So here we have a polynomial function. F of x is equal to x squared plus 9x plus 2. And we're going to go ahead and plug it into our formula. So we have f prime of x is equal to the limit of f of x plus h minus f of x over h. And we're going to go ahead and plug our values in. All right. So first of all, we want to go ahead, break it up as before, and we want to go ahead and plug it right back in. So we already know what f of x is. F of x is given to us, so we don't have to sit and figure that out. What we need to do is figure out f of x plus h. So f of x plus h, we're going to go ahead and plug in x plus h wherever there's an x value in our original equation. We're going to go ahead and we're going to FOIL distribute those values through. All right. And we're going to go ahead, and once we go ahead and do that, we're going to get x squared plus 2xh plus h squared plus 9x plus 9h plus 2. And wow, that's a lot of numbers. All right. We're going to go ahead and do the subtraction for the top separately. We're not going to plug it into the formula yet. And so we're going to go ahead and take what we just got for f of x plus h, and we're going to go ahead and subtract f of x. Now, when we do that, remember, we're subtracting a polynomial. So when we subtract a polynomial, remember, we have to go ahead and put that polynomial in parentheses. And what's going to happen is we are going to be changing the sign of all the pieces in that second polynomial. So when we go ahead and do that, this is going to become negative x squared. And this negative x squared is going to cancel out with the x squared in front. This is going to become negative 9x. This negative 9x is going to cancel out with the 9x over here. We're going to have a minus 2 now, it's not a plus 2. And that minus 2 is going to go ahead and cancel out with the plus 2. And whatever's left over is what we're going to go ahead and write down. So what's left over is all our terms basically with h in it. So we get 2xh plus h squared plus 9h, and the order doesn't matter. You don't have to worry about putting it in any kind of descending order or anything. Now what we're going to do is we're going to take this top portion, we're going to plug it into our limit and over our denominator h. Now we can go ahead and factor out an h from the top just like we have been doing. And those h's are going to cancel out. So this denominator is going to cancel out with the h's we factor out from the top. So we're looking for the limit of 2x plus h plus 9. And remember, as h approaches 0, this middle h is going to disappear. So we're just left with 2x plus 9. All right. So now that we have our derivative function, we can go ahead and plug our different values into it that we were asked to. And the first one we were asked for was f of -2. So if we plug f of -2 in, we get -4 plus 9, which is just equal to 5. When we go ahead and plug 0 in, we just get 2 times 0, which is 0 plus 9. So we're just left with 9. And then if we go ahead and plug 3 in, we get 2 times 3, which is 6, plus 9, which is 15. right? Our second function here, we have 12 over x as our function. And we want to do the same thing as we did before. Wherever there's x, we're going to plug in x plus h. Now this is going to be a little interesting because x is in the denominator of this fraction. So if we go ahead and plug that in, our f of x plus h is 12 over x plus h. We didn't really have to do a lot of work there, right? What's going to happen is then we have to go ahead and subtract it from 12 over x, which means now we have to go ahead and get a common denominator in order to perform this subtraction. So our common denominator in this case is x times x plus h, which means that now this first fraction gets multiplied by x, what leaves us with the 12x. We're going to subtract 12, and we needed to multiply this fraction by x plus h. And so there's our x plus h. Then we can write it as one fraction. From here, we have to go ahead and distribute, and we're going to see that our 12x's cancel out, and we are left with negative 12h on the top, and x plus h times x on the bottom. And notice the negative stays. Don't forget to don't drop your negative, right? And so this is our function. Now we have to take this top portion, and we have to go ahead and plug it into our limit function. All right, which means we have a fraction within a fraction. All right, and so when we have a fraction in a fraction, remember our rule for fractions is we keep the top, change the sign to multiplication, and flip the bottom. Now remember, this bottom is a whole number that's h over 1, so it becomes 1 over h. And when we go ahead and multiply those two things, now this h is going to cancel out with this h on the top. And I'm not going to go ahead and distribute the x through this x plus h. I'm just going to go ahead and leave it. Again, your negative sign remains, and I'm left with 12 over x plus h times x, or you can have the x in the front right over here. It doesn't matter where that x is placed. And so therefore, our limit as h approaches 0, because we aren't done yet just because we got our fraction, this h is going to go to 0. All right, and so we're left with negative 12 on the top and x times x on the bottom, which is x squared. And this represents, this negative 12 over x squared represents our derivative. All right, we're going to go ahead and plug our values in. So at negative 2, we get negative 2 squared, which is positive 4. 4 divided by 12 is 3, but there's a negative on the front, so we end up with negative 3. With 0, 0 makes it undefined because 0 would be in the denominator of our fraction. And if we have 3, then we just go ahead and plug our 3 in there. 3 squared is 9. 12 over 9 simplifies to 4 over 3, and we keep our negative sign. So you may want to practice writing out some steps with different functions. You're going to find some shortcut rules in the next chapter, which is going to help you go a little quicker than using this way of doing it. But make sure you practice writing out your steps using the h's. Make sure that you're not dropping any terms or your negative sign. All right. And in order for this derivative to be defined, remember the function has to be continuous at a point. If it's not defined at a point, if it's discontinuous, if there's a whole vertical asymptote or jump, all right, then it's not differentiable. All right. So all functions are also not differentiable if a tangent line is vertical at a point on the function. Okay. And this usually happens if you have some sort of sharp point where the graph sharply comes up and comes down like this. And you can see that if we go ahead and try at this point, we're going to have that straight up and down problem. Or if the slope of the function is actually really just steep to begin with, and when we have that particular point going on, it forms that vertical line. So we're going to